In today's video, we're going to take what we learned in last class's video and put it together with some of our previous knowledge to learn how to sketch curves using our knowledge of calculus. So we're going to look at first the relationship between the function, the first derivative, and the second derivative. So we're going to do this by working through examples today. So in this graph, I have you the graph of the derivative of a function on a closed interval from -4 to 4. And I want to figure out what this graph tells me about its original function. So first off, on part A, it asks us to find the intervals in which the function is increasing or decreasing. So to find out the intervals in which the function is increasing, that's where the derivative, or when it's decreasing, that's where the derivative is less than 0, and increasing, and when the derivative is greater than 0, our function is increasing. So let's see, when is our derivative less than 0? It's only this highlighted area, because that means our y values, which is what's being measured, our derivative is what's being measured on the y-axis on this graph, is negative. And so my only interval will be what's highlighted here. So that would be from -4 to -3. Now we have to translate this into words about what that tells us. Now, since the derivative was given to us, we're going to explain our reasoning using our derivative. So since the derivative of f of x, all right, we could conclude that f is decreasing on the interval from -4 to 3 because of the following information. Because, or since, f prime was less than 0 in that interval. That's all we knew, so we've explained how we knew. Okay, next part of the question was asked, where is the interval increasing? Well, interval is increasing whenever the derivative is greater than 0. Now, notice I drew an open circle at 2. Well, at 2, the function is neither increasing nor decreasing. The actual derivative, f prime of x, is equal to 0 because it's on the x-axis. So we can't include that, so we have to jump over it when we find our intervals of increasing. So f is increasing from -3 to 2, union 2 to infinity. Or 2 to 4, sorry, because this is a closed interval. And how do we know that? Well, that's because f prime is greater than 0 on this interval. Now let's look at what interval is the graph of f concave up or concave down. So we're given the derivative. And remember, in order to find concavity, we look at the second derivative. Well, to find the second derivative, we take the derivative of the first derivative. So it's the rate of change of the first derivative, or remember, derivative stands for slope of the secant lines, or slope of the tangent lines. So it would be, to figure out the second derivative, we're going to look at the slope of the tangent lines of our derivative graph. I would say my second derivative, or the slope of my tangent lines, is increasing from -4 to that 1/2, and then from -4 to -1 1/2, and then from 2 up to 4. So what I have highlighted is where my derivative function is increasing, which is where my second derivative is greater than 0. So how to explain that? Because we do have to justify our reasoning. The graph of f would be concave up on our interval from -4 to -3/2, and from 2 to 4, since our derivative, f prime, is increasing over this interval. So concave up, when you look at the first derivative and figure out when the first derivative is increasing, and that correlates to concave up for our original function. Now we want to figure out when the derivative is concave, when the function is concave down, and that would be when my first derivative is decreasing. So the graph of f is concave downwards on the interval from -3/2 to 2, since f prime is decreasing over this interval. And that will be enough. So again, notice I'm referring back to my justifications from what was given, which was our first derivative. All right, C, at what x-coordinate does f have a local extrema? All right, so remember, by definition, our local maxes and mins occur when our first derivative equals 0 or does not exist. So in order to look at our derivative graph to figure out when our original function has a local extrema, we just need to figure out our x-intercepts of our derivative graph, which will be at -3 and 2, because that's when our derivative is equal to 0, and any undefined points on our derivative graph. And this one doesn't have any undefined points. So those would be our only two extremas. Now we need to classify these extremas as maximums or minimums. All right, to recall, so we figured out it's a local maximum if we are increasing and then decreasing from that critical point. So increasing up to the critical point, decreasing after the critical point. So that translates to my graph. That means the f prime needs to be positive, critical point, then f prime needs to be negative. Now, if I wanted to find a local minimum, remember that was decreasing and then increasing. Decreasing translates to our derivative graph is when our derivative graph is below the x-axis or less than 0. And when our derivative graph is positive, our function is increasing. So on our first one here, our derivative graph changes from negative to positive at x equals -3. The function has a local minimum at x equals 3. Again, I'm referring back to my derivative to explain this. Okay, so notice that I'm not going to include 2 as a maximum or minimum point of relative extrema because it is positive. Our derivative is positive to the left of that critical value and positive to the right. So the only other possibilities of local extremas will be at our endpoints. And so we need to figure out if -4 is a local max or a local min. And you kind of just do rational thinking about this, okay? We have the point -4, and then our derivative is negative after that, because, our derivative is negative, which means our function is decreasing. So if we have our endpoint and our function decreases from that endpoint on until it gets to that -3, then that must be a local maximum. So that's all we're going to translate right here. So since the function is decreasing away from the left endpoint, then x equals -4 is a local maximum to our graph. Now notice on the other endpoint, our derivative is positive, so we're increasing up to that point. So if we're increasing up to that point, 4 is also a local maximum. So since the function increases up to the right endpoint, x equals 4 is a local maximum. So this graph has 2 maximums and 1 minimum. Okay, next thing we want to look at is the x-coordinates of the inflection points of our graph of f prime, our graph of f of x. So let's see. Okay, inflection points occur when the second derivative is equal to 0. Okay, or when the inflection points actually occur when the second derivative is equal to 0 and it switches from concave up to concave down. Now, if you remember, when we looked at this and found our intervals of concave up and concave down, we noticed it changed here at the turning points of our derivative graph. And so, because that's when our derivative, our slope of our tangent lines of our derivative graph, so that's the second derivative, equals 0. And that would be at our turning points. So the translation to this is anytime you want to flatten your inflection points, first you're going to locate all the turning points of your graph. And the turning points will always be inflection points because in order to make that curve there, we're going to switch from increasing to decreasing or decreasing to increasing on our derivative graph, which means our second derivative switches from concave up to concave down or vice versa, concave down to concave up. So all I have to write is there's an inflection point on the graph of f has the same x-coordinates as the turning points of x. Namely, on this graph, our inflection points would be at -3/2 and at 2. Now notice this, we're given a lot of information about the x's and about intervals in which the x is increasing, decreasing, concave up, concave down, local max, local mins. We found the critical values of our original function, which I'm plating here. And we also found our inflection points, or points of inflection. Those are going to be our starting points on sketching the graph of this function, and then we're just going to add in our concavity. So what I'm going to do is I'm going to take these critical numbers, inflection points, and I'm going to make a new sign chart. This sign chart that we'll be using in today's graph kind of puts the other 2 sign charts that we learned last class together as one. So I'm going to start by labeling our critical numbers and our points of inflections on our sign chart. Now, since this is a closed interval, I'm going to go ahead and label our endpoints and make them special as well. And then this sign chart only talks about the function. So I'm going to look at that first interval from -4 to -3. And we'll look at my data I got up here. And we've already figured out that from -4 to -3, our derivative was negative, which means our function was decreasing. So I'm going to write that on my sign chart. So this interval, it's decreasing. And then we figured out our slope of our tangent lines to our derivative graph, or second derivative, was positive. So a second derivative is positive means that we have concave up. So in this interval, I need to draw a decreasing concave up curve. Then I'm going to go from -3 to -3/2. And we're going to look at this piece of the graph. All right, our graph is above the x-axis. So that means our derivative is greater than 0. And our slopes of our tangent lines are all positive. So, sorry, I got ahead of myself. So that's increasing. And the slope of our tangent lines are all positive. And so that means our second derivative is greater than 0. Which means it's concave up. Now I'm going to go from inflection point to inflection point. So we're going to go from -3/2 to 2. Now looking at our function here, our derivative is above the x-axis, so that means our original function is increasing. And our slopes of our tangent lines are negative, going down. And so that means our second derivative is negative, which means it's concave down. And then the last interval from 2 to 4, our function is above the x-axis, our derivative function above the x-axis. That means our first derivative is positive, which means our original function is increasing. The slopes of our tangent lines are positive, which means our second derivative is greater than 0, so we're concave up. So increasing, concave up. All right, so then I'm going to draw the little shapes of these. So there's concave up and decreasing, concave up and increasing. What does a concave down increasing look like? And then finally, what an increasing concave up looks like. Because when you take the derivative, you lose that constant, this derivative is just going to be one possibility. You might not have the exact same possibility. So where you start your first point is up to you. I chose to put my point here at 4, and I'm going to go down to this point of 3. It doesn't matter. Notice I don't even label anything on the y-axis. That doesn't matter. And I'm just going to connect those two dots with our concave up decreasing. Now I'm going to connect dots with concave up increasing. Then I'm going to continue to increase and do concave down until I get to 2. And then after 2, we're going to continue to increase, but this time I'm going to switch my curvature to concave up until I get to 4. And so this is what the graph mainly will look like, that basic shape. Now yours would differ, it'd be curved down or curved up based on how much you went up or down. So there's many choices on this because we don't have any knowledge about the y's of the original function, but we can get a basic kind of curvature or shape of the graph. So this is not the only possible solution, but is one. Okay, now I'm going to let you try one. I'm going to kind of break this up from A, B, and C. So I want you to start, here's the graph of the derivative function, and I want you to find the intervals in which f is increasing. We call f is increasing when our derivative graph is above the x-axis. So what I have highlighted here is where my derivative is increasing. Where my derivative is positive means where my original function is increasing. So I could say f is increasing on the interval from -2 to 0, union 1 to 3. And my reasoning is since f prime is greater than 0 on this interval. F prime is positive on this interval. Now I didn't ask you to find where it's decreasing, but the unhighlighted points are where the graph is decreasing. On what intervals is the graph of f concave up? Okay, so concave up happens when the slope of the tangent lines to the first derivative is positive. So that's what I'm looking at. Or another way to think about that is when my first derivative is increasing, my second derivative would be positive. So I'm going to draw when my first derivative is increasing. And that's when my original function was concave up. So reasoning for this, so f is concave up on the interval from 0 to -3/2. -3 to -3/2. Union 1/2 to 3. And my reasoning for this is since the derivative is increasing over these intervals. Okay, now in C, find all the x-coordinates of the local extremas and classify them. So to find my local extremas, that could happen at my critical values or at my endpoints. So I went ahead and plotted and noted my critical values and my endpoints on the graph. Those are what I've highlighted in blue here. Okay, all these points are where my possible extrema values could occur. So that's the first thing you're going to derivative graph, be able to identify your critical points and your endpoints to find possible points of max or mins. Now I noticed that in between this critical value of -2, my function is switching from, my derivative is negative to positive. So that is going to be a local minimum. And then at 0, my function switches from positive to negative, my derivative switches from positive to negative, which means my function switches from increasing to decreasing. So I have a local maximum. And I also have an extrema here at 1 because my derivative switches from negative to positive, which means my function switches from decreasing to increasing. So that makes it a minimum. Now let's look at our endpoints. So f prime of x is increasing up to my right endpoint, so that's positive. And then my f of x, my function is decreasing away from my left endpoint, which makes it also a maximum value. So this time our maximums are all our endpoints are both maximums. All right, so let's write that all up. First, I'm going to talk about the critical values that are local minimums. So f has a local minimum at x equals -1 and x equals 1, since f prime changes from negative to positive at these points. Next, let's talk about the minimum, the critical value that has a minimum. So I say f has a local maximum at x equals 0 because the derivative switches from positive to negative at this point. And last but not least, let's talk about our endpoints. So f has a local maximum at x equals -3 and at x equals 3. Because for x equals -3, our function is decreasing away from our left endpoint, and at x equals 3, our function is increasing up to our left endpoint, our right endpoint. Okay, what are the x coordinates of your inflection points at the graph of your derivative? Okay, so you're asked to find the x coordinates of the inflection points, okay, of the points of inflection. Those occur at your turning points of your derivative graph. So these 2 points that I have highlighted here are our points of inflection because they are the turning points on our derivative graph. And that's all we have to do to write our explanation. So I wrote that the inflection points of the graph of f has the same x coordinates as the turning points of f prime of x. Namely, in this case, at x equals -3/2 and x equals 1/2. Last but not least, we're going to sketch a possible graph. So now I need to draw a number line and put all the information that we have together on, a sign chart, and put all the information we have together on the sign chart, and then use this data in order to sketch our graph. So remember, our sign chart, we're going to put our endpoints if it's a closed interval. In this case, it's -3 to 3. Then we're going to put our critical values and all our points of inflection. So we found up here that our critical values of our original function are the x-intercepts of our derivative graph, or when the derivative graph does not exist. So in this case, we only have x-intercepts. So I'm going to label my critical points at -2. Then I have a point of inflection, my turning point here at -3/2. Then I have a critical value at 0. Another turning point at -1/2, and then another critical value. Oh, I need more room. Another critical value at 1, and then of course our endpoint at 3. Whew, okay, so that's the number of points. So I'm just going to look at this piece by piece on my graph. So I'm looking at my derivative graph and translating that to what it tells me about my original function. Let's start the interval from -3 to -2. So let's highlight that on our graph here, -3 to -2. Well, first thing I know is the derivative is below the x-axis, so my derivative is less than 0. And if our derivative is less than 0, that tells us f is decreasing. And if our second derivative, here our slopes are positive, that tells our function is concave up. Just realized I wrote increasing. I think I said decreasing, didn't I? All right, so we're decreasing and we're concave up. Okay, next we'll look at the interval on our derivative graph from -2 to -3/2. All right, I'll highlight this in orange. Now, our graph is above the x-axis, so that means our derivative is positive. If the derivative is positive, our function is increasing. And then our slope and tangent lines are still positive, so we're still concave up. So this interval will be increasing concave up. Okay, now we're going to look at the interval from -3/2 to 0. Okay, our graph is still above the x-axis, so our derivative is positive, which tells me my original function is increasing. Our slopes of our tangent lines are negative this time, or my derivative is decreasing, so it tells me that we're concave down. So this function will be increasing, concave down. I forgot to draw the curves. Now I'm going to look at the interval from 0 to 1/2. I'll highlight in pink. Okay, our graph is below the x-axis, so that means our derivative is negative, so our original function is decreasing. Our slopes of our tangent lines are negative, and so my second derivative is negative, so my graph is concave down. So this interval will have decreasing concave down curve, which looks like this. Okay, in green, I'm going to look at the interval from 1/2 to 1. My graph is below the x-axis, so my derivative is negative, which means my function is decreasing. And the slope of my tangent lines are positive, so I'm concave up, so decreasing, concave up. And now our last interval. So looking at the graph from 1 to 3, my graph is above the x-axis, so that means my derivative is positive, which means my original function is increasing. My slopes of the tangent lines to this derivative is positive, so that means my second derivative is positive, which means my original function is concave up. So this interval will draw increasing, concave up. So again, you can randomly pick where you're going to start your left endpoint. Just remember that it is an extreme of values, and it's a local maximum. So I'm just going to pick a random point to start at. That's the reason, again, we haven't labeled any y-axis values because we don't know what y values we're going to use. So I'm going to start up here. And then I'm going to draw a concave down decreasing curve until I get an x of -2, which I'm going to put way down here. All right, now I'm going to draw from -2 to -1 1/2 a concave up increasing curve. And now from a -1 3/2 to 0, I'm going to draw still increasing, but this time I'm going to switch my concavity to concave down. And then until 1/2, I'm going to continue concave down, but now I'm going to be decreasing. Until x equals 1, I'm going to be continuing decreasing, but I'm going to switch to concave up curve. And then from 1 to 3, I'm going to be increasing concave up curve. And this is one representation of this function. It'd be similar, but it could be moved up and down, left and right, or stretched out some. Okay, and the second way you're going to see that is from a table of values or just a list of information. So you're going to get a list of information and you're going to have to figure out what the graph looks like, a possible graph. So what you're going to do is you're going to start by drawing a sign chart. The sign chart of the function is going to be very important to sketching the graph. But this time I got to figure out where my critical values are in my points of inflection. Well, it tells us in this case that our derivative is equal to 0 at 0 and 4. So that is their critical values. So those are two numbers I need to flag on my graph here. Now remember, our points of inflection is when our concavity switches from positive to concave up to concave down. And I noticed that my second derivative switches from positive to negative at x equals 2. So that means x equals 2 is a point of inflection, and so I need to add that value to my sign chart. Okay, now I'm going to look at the given information on each of these intervals. So I'm going to start from -infinity to 0 and see what I know about the first derivative and the second derivative over that interval. So I noticed that they told us that our derivative is positive from 0 to 4. So from 0 to 4, our derivative is positive, means our function is increasing. So I'm going to label on my graph here, on my sign chart here, that from 0 to 2, my function is increasing, and from 2 to 4, my function is increasing. So both of those intervals need to be labeled with increasing. The next bit they gave us is f prime of x is less than 0 for x is less than 0 and x is greater than 2. So f of x is less than 0 means negative. So our derivative is negative, which means our original function is decreasing. So I'm going to label my interval from x. Oh, that should be less than. I think I read less than. That's a typo. I think I fixed it on your version though. And x is greater than 4 is also decreasing. So now I figured out my intervals in which function is increasing or decreasing. Now I'm going to look at my second derivative, figure out my concavity. So they tell me that the second derivative is positive when x is less than 2. So if second derivative is positive, that means my function is concave up. So all intervals less than 2, I'm going to label with concave up. Then they told us that our second derivative is less than 0 from x as greater than 2. So when the second derivative is less than 0, it's concave down. So all intervals greater than 2, I'm going to label concave down. Now let's put our shape of a graph for each of these. So I'm going to draw a concave up decreasing curve, a concave up increasing curve, a concave down increasing curve, and a concave down decreasing curve. Now, unlike the last example where I could start wherever I wanted to, this one gave us a couple of points that we need to plot on our graph first. And that's what I haven't highlighted yet. They gave us f of 0 equals 0, f of 2 equals 3, and f of 4 equals 6. So they gave us a few points. Actually, they gave us our critical values and our inflection points for us to actually sketch on this graph. So I'm going to plot the point 0, 0, 2, 3, and 4, 6 on my graph. Now that I have those points plotted, I'm going to use the sign chart to sketch the rest of the graph. So when I was to the left of that point 0, my function is always decreasing and concave up. So I'm going to draw a decreasing concave up. I guess I'm going to label these as max or min, so it helps you when you're sketching the graph. So I have a local minimum, a point of inflection, and then we have a local maximum. So for the interval from x is less than 0, I need to draw concave up decreasing until I get to that minimum value of 0, 0. Okay, after that, I now have a concave up increasing curve until I get to x of 2, or that point of inflection we have plotted at 2, 3. And then I'm going to draw a concave down increasing graph until I get to x equals 4. And then after x equals 4, I'm decreasing concave down. And there you go. We've used this table of values to sketch our graph. You try the next example. Okay, you need to start by making your sign chart. Notice that our second derivative is less than 0 for all x values except x equals 4. And the derivative at 4 does not exist. So that tells us 4 is a critical number. So I'm going to plot that on this value here, on this sign chart. And I also noticed that my second derivative switches from negative to positive at x equals 4. So this sign chart only has one value. That critical number happens to be a point of inflection on this graph. And there's no other critical values. Interesting. So I'm going to break this up to all values less than 4. So let's see what the first derivative tells us for all x values less than 4. Well, the first derivative says x is less than 0 for all real numbers except at 4. So if our derivative is negative, that tells us our original function is decreasing. So everywhere except 4, our function is decreasing. So I'm going to label birth intervals as decreasing. Now let's look at concavity, which are the second derivative. The second derivative is less than 0 from negative infinity to 4. Now if the second derivative is less than 0, that tells me that the function is concave down on the interval from negative infinity to 4. And then we're also told that the derivative is positive from 4 to infinity. So if the second derivative is positive, that tells us our graph is concave up. And we didn't have a starting point. I didn't give you any points on this information. So this graph could vary up and down quite a bit and stretched out quite a bit. So all you have is that you have a point of inflection of x equals 4. So randomly choose to put a dot somewhere where you have an x value of 4. So I'm going to put it here. And then to the left of that, approaching that x value of 4, I need to draw a decreasing function that's concave down. And after the 4, I need to draw a decreasing function that's concave up. So it could look something like this. Okay, I've given you the graph of the first derivative, and I'm going to ask you to draw the original function. So again, always start with finding your sign chart. We have a critical value at 1. My derivative is above the x-axis, so that means my function is increasing from negative infinity to 1 and also from 1 to infinity. So this function is always increasing. My slopes of my derivatives are less than 0, so that means it's concave down up until the 1, but then my slopes of my derivative or my second derivative become positive, and so it switches to concave up. So I'm just going to draw the graph here on this graph. You would do it on a separate graph. So I pick a dot, then I'm going to do when at that point of inflection, and I'm going to draw increasing concave up to that point of inflection, and then increasing concave down up to the point of inflection, and then increasing concave up to after the point of inflection. So it's just a cubic graph. All right, now I want you to do the same thing to this second graph here. This graph has two critical values. One is at 1 and the other is at 3. And it has one point of inflection because that is a point where it's a turning point of our derivative graph. So remember, critical values are x-intercepts of our derivative graph, and points of inflection on our original function is represented by the turning point of our derivative graph. So I've divided this up to 4 sections. So I'm going to start with the numbers less than the interval from negative infinity to 1. And my derivative is negative. So therefore my function is decreasing. And the slopes of my tangent lines are positive, so my second derivative is positive, so my original function is concave up. And then my next interval is from 1 to 2. And here my derivative is positive above the x-axis, so that tells me my original function is increasing. And the slopes of the tangent lines are also positive, so my second derivative is positive, which translates to concave up. My third interval is from 2 to 3. Okay, my first derivative is positive because it's above the x-axis. My second derivative is negative because the slopes of my tangent lines are negative on this interval. So my original function is increasing and concave down. And my last interval, 3 to infinity. My derivative is negative, so that tells me, and my second derivative is negative. My slopes of tangent lines are negative, so that tells me my original function is decreasing and concave down. So now I'm going to put those four intervals together to sketch my graph. All right, so I have a critical value, I have a minimum value at 1. I have a point of inflection at 2, and I have a maximum value at 3. So I'm going to start by plotting a dot on my graph for at some x value of 1. You can put that anywhere you want, and I need to go from the left of that, decreasing concave up to that point. And then from 1 to 2, I'm going to do concave up and increasing. From 2 to 3, I need to continue to increase, but concave down. and from 3 to 4, decreasing, concave down. Concave down. And so your graph should look something like this, again, where those points are, where your max mins and where your max mins are, and along the y value change. Okay, now we're going to go the other direction. This time I'm giving you the graph of the original function, and I want you to find the graph of the derivative. So this is the graph of our function. Now we're going to start this very similar to how we started the other direction by drawing a sign chart. This time we're going to put x and our derivative on the sign chart. So first thing we have to recognize is we have to find our critical numbers and plot those on our graph. So remember, our critical numbers are where the derivative does not exist or the derivative equals 0. So here we have a sharp turn, so the derivative does not exist. So that is a critical value at x equals 0. Next, we have another sharp turn at f equals 1, which again, the derivative does not exist. So it is a critical number, which I will plot on my sign chart. Finally, we have where the derivative is equal to 0, which is this local maximum here, and that'll be a critical value as well at 1/2. Then I would look and see if I had any points of inflection when the concavity switches, but I don't have that in this case. So now I've divided our sign chart into 4 sections. So we're going to start with the first section, which is all numbers less than 0. I'm going to look at the graph and identify what can I know about the derivative. Well, since the function is decreasing, that tells me the derivative is negative. Next, I notice that the function value is concave up. So that tells me that my derivative is increasing over this interval. Because remember, if our slope of our tangent lines to the derivative graph was positive, we had increasing and concave up. So I have my derivative is increasing over this interval. Okay, next I'll look at the interval from 0 to 1/2. Okay, first I ask myself, this function is increasing over this interval. So if the function is increasing, then my derivative is positive above the x-axis. And my function is concave down. So that means my derivative must be decreasing. Moving on to section 3, from 1/2 to 1. My function is decreasing, so my first derivative is negative. And my function is concave down, so my first derivative is decreasing still. And then looking at the last section, my function is increasing, which translates to meaning my derivative is positive. My function is concave up, so that means my first derivative must be increasing. Okay, so I have the basic information that we have increasing and negative or above the x-axis, below the x-axis. But for derivatives, going from the original function to the derivative graph, we need a little bit more information. So we need to figure out about where to start. And to do this, I'm going to look at these sharp turns, because sharp turns on the original function translates to a jump discontinuity on my derivative graph. So I need to figure out how far I have to jump to do this jump discontinuity. The best way to do that is to choose a point pretty close to that sharp turn and then find the slope of the tangent line on our function to kind of give us our value, our derivative value close to that sharp turn. Now I'm just going to estimate. These doesn't have to be exact. I'm just kind of doing some kind of ballpark estimate because there's no way that we can draw these perfectly. It just gives us sort of a broad idea of where to put these values. So I'm looking like I'm going about half over, and it looks like I'll go about down. I'm almost 1. And so rise over run, I'm going down 1 and over 1/2. And so that gives me, when I flip and multiply, -2. So that means that just to the left of that point 0, I'm going to have a function, my derivative is going to have a value of about -2. So I have that gives me a point to plot on my derivative graph. Next, choose a point about the other side of the sharp turn and figure out the slope of this tangent line. Again, we're just going to estimate. Again, just doing a random estimate here. It looks like I've run across about 1 and up about 1/2, maybe 2/3, depending on how you want to look at it. So I'm just saying about 1/2. So that tells us that on this side, our slope is about 1/2, and it's a positive slope, so that's a positive 1/2. Okay, I don't have to worry about the critical value of 1/2 because that is, I know that has to equal 0 because the slope at that point is 0. So that one's easy to do. So now I need to figure out the slope on each side of our other sharp turn, and we're just guesstimating here. So I'm drawing my tangent line to that point just to the left of our sharp turn. Again, just guesstimating, estimating. I don't expect to be exact. Just gives me a kind of ballpark idea of what to be at. And so I'm going to estimate this slope to be about 1. And it's negative because the line is decreasing. So I'm going to have a y value of about -1 at this one, at the critical value x equals 1, just to the left of it. Now just to the right of it, I'm going to repeat this process one more time. And I guesstimate the slope to be approximately 2. So that gives me my jump discontinuity when I sketch the graph. So now I have all the important information. We're ready to sketch the graph. You would sketch this on a separate graph, but because of the lack of room here, I'm going to graph it on this one here. But I do need to go down to -2, so I need a +2. So I'm going to just kind of extend this graph a little bit. All right, so I'm drawing an open circle at the x equals 0 for that first critical number because, again, it does not exist at this point, so I can't include it. And I'm going to draw an increasing, I'm going to start negative, and it needs to be increasing kind of graph. Now, since there was concavity, I'm going to draw a little slant there. Next, I'm going to do on the other side, the jump discontinuity jump to about 1/2. And then after 0 to 1/2, I am positive and decreasing. And we're going to decrease to, at x equals 1/2, I have a slope of 0. So we're going to go down to the 0. Okay, from 0 to 1, the green interval, I am negative, so below the x-axis, and my line is decreasing. And I'm decreasing to about a slope of -1. And that's what we figured out. Now I've jumped on discontinuity. I'm going to jump up to a slope of 2 at x equals 1. And then after that, I'm going to continue to increase, and we have our positive value. So this is sort of like what this graph would look like. The derivative of the graph of this function would look like. All right, now it's your turn. I'm going to pause and let you try to figure out the graph of the derivative that's given here in the second diagram. Okay, remember this is the graph of the original function. So our critical values are at our local max and min points. That's where our derivative is equal to 0. And in this one, we don't have any derivative that does not exist because I'm looking for sharp turns or vertical tangent lines, which I don't have here. Those are when that derivative does not exist in the original function. So I'm going to flag x equals about a -2 and x equals +2. Again, you could be a little bit more exact if you want to, as critical values. Next, I want to look and see where the concavity switches and plot the point of inflection on my sign chart. So I can notice that I have concave down graph starting from the left end of the graph to about x equals 0. Then it switches over to concave up. And the rest of the graph is concave up. So that means at x equals 0, I have pretty much a point of inflection. So that number needs to be placed onto my sign chart. That important value. All right, so my sign chart, again, remember the bottom numbers are x values on my derivative graph, and what I'm about to put on the top of the sign chart is what I know about the derivative. So that will help us sketch the graph. I've divided this up into 4 equal intervals, so let's start with numbers less than -2. All right, so in our original function, this is the part that's from numbers less than -infinity to -2. So my function is positive here, is increasing, so that tells me my derivative is positive. My function is concave down, so that tells me my derivative is decreasing. On my next interval, from -2 to 0, my graph of my function is decreasing. And since the graph is decreasing, that tells me that the derivative is negative. And my function is concave down, which tells me the derivative is decreasing. From section 0 to 2, my function is decreasing, so my derivative is negative. My function is concave up, so my derivative is increasing. In our last interval, from 2 to infinity, my function is increasing, so that tells me the derivative is positive. My function is concave up, which tells me my derivative is increasing. So we have some basic information. Now remember, at the critical values -2 and 2, my function value is 0, because remember, critical values, local max and mins, are represented by x-intercepts on our derivative graph. And my point of inflection will be represented by a turning point on my function graph. My derivative graph, sorry, my derivative graph. All right, so let's plot those x-intercepts. So those critical values, when x is -2, my derivative is 0. When x is 2, my derivative is 0. So we have those two plotted. So we need to figure out where that critical, that turning point is going to be on our new graph. So let's figure out where that turning point is going to be on our derivative graph. So we're going to do that by figuring out the slope of the tangent line at that turning point, or at that point of inflection. So here I'm going to just sketch it. And again, this is just going to be an estimate. It doesn't have to be exact. And so I'm just going to estimate what our slope looks like. And it looks like I go down 2 and run across 1. So that gives me a slope of -2. So that tells me at x equals 0, my function, my derivative, will have a value of -2. So that'll give me the point to plot my turning point, my local minimum of our derivative graph. Now I have those 3 points. I'm going to look at the data from the sign chart and just connect these dots. Okay, I want to start from -infinity to -2. Looking at this, I see that my derivative graph needs to be positive above the x-axis, but it needs to decrease until it gets to that point of -2, 0. Now the red interval, we're still negative, so it means we're below the x-axis. The graph is decreasing until I get to that turning point. And in the green interval, I need to continue being negative, but I'm going to increase my line until I get to that critical value. And then for the purple interval, I'm increasing and positive. And there you go. We have now sketched the graph of the derivative given the original function.